With a few exceptions, we've focused primarily up till now on quantum mechanics in just one spatial dimension. But obviously one needs to extend that into three dimensions to realistically describe particle motions in the realm that we usually observe things in. And so let's move on to quantum mechanics in 3D. It's mostly a straightforward generalization to 3D, and it's particularly straightforward in the Schrodinger wave mechanics. And so let's take a look at that. In the Schrodinger wave mechanics in one dimension, we had a wave function psi of x and t that only depended on a single dimension x. Well, pretty obviously we can extend that to three dimensions by incorporating x, y, and z for the location variable. And I'll use shorthand notation usually for this and call that r vector. So you can think of this r vector as x, y, and z if we're in Cartesian coordinates. However, we'll also want to allow for the possibility that maybe we're using spherical coordinates or cylindrical or some other coordinate system. And if I use the spherical coordinates, well, then this r vector here would represent r, theta, and phi for the coordinates in spherical coordinates. Kind of similarly, in one dimension, the classical momentum of a particle went over into a momentum operator, which was h bar over I partial with respect to x. And that extends naturally, as we've already seen, really, to a particle in 3D really has to be, you have to give the components of the momentum vector, and the components of that in Cartesian are turned into operators that are h bar over I partial derivative with the respective variable. In the case of y, it's partial with respect to y. The z momentum operator is h bar over I times the partial with respect to z. Oftentimes we'll use these, but again, the way I kind of like to look at it is the momentum vector, classical, it's just simply a vector, goes over into quantum mechanics as a momentum vector operator, which I'll sometimes write with the hat over it. And if you look at that, that's just h bar over I, and these are the components of the gradient, so a gradient operator. So it goes over into h bar over I times the gradient operator. Again, this is a little bit more general because I can express the gradient not just in Cartesian coordinates, but also in spherical or cylindrical or a number of other coordinate systems. So a little more general notation. The momentum operator goes over into this term proportional to the gradient. The time-dependent Schrodinger in three dimensions, we know what that looks like classically, so we can extend things using that usual substitution. It goes into a Hamiltonian operator operating on the 3D wave function is equal to IH bar partial with respect to t of the 3D wave function. And remember, the Hamiltonian is essentially classically the total energy, the kinetic energy plus potential energy. And in quantum mechanics, as we've seen, p vector becomes p operator vector, and r vector actually becomes r vector operator. But remember, p is the gradient, and so this is really del dot del with some constants in front of it. H bar over I is minus h bar squared, and then I still have the 2m. And del dot del, the divergence of the gradient, is the Laplacian del squared. Okay. And as usual, the x, y, z's just turn into the coordinates, so you don't have it's just multiplication by the coordinates. So the potential energy is essentially the same in classical or quantum mechanics. And you put all that together, this becomes the Schrodinger wave equation in three dimensions for a particle moving in a potential that does not depend on time. Okay? That's the usual case. And so very, very similar. In one dimension, this Laplacian just turns into the second derivative with respect to x, partial with respect to x squared. And so it reduces nicely. The interpretation of psi is as that it's a square is a probability density, and that's the Born interpretation of the wave function. And we actually did this in some detail earlier, but in one dimension, it was the probability that m at time t is in the region of space x between x1 and x2. Well, all we have to do now is to make sure that it's the probability that it's in a volume region. So I keep it a region, but it's really the volume that's bounded by, in the x direction, by time these specific values x1 and x2, y from y1 to y2, or z from z1 to z2. And it was originally in one dimension was just a single integral, so now we have to integrate over all three dimensions in Cartesian coordinates anyway, of the absolute modulus squared. So this is the wave function squared, and we integrate over those three regions to get the probability of finding the particle inside the box that's bounded by x1, x2, y1, y2, and z1, z2. If you look at this, and look at the units, the wave function in three dimensions, or wave function squared, I should say, has units of inverse meters cubed, because this will have units of meters cubed, and so I'll need to have this be this whole quantity here, inverse meters cubed, because I know probability is simply a fraction, is dimensionless. So the units are a little bit different in three dimensions. Another way, and in a lot of ways I like this one better, and that it boils it down to an infinitesimal. The probability that the mass m at time t is in the volume dv, which is dx dy dz if we use Cartesian coordinates, centered at r vector, is just the wave function squared, absolute modulus squared, times the volume. So if I want to know what's the probability of finding the particle in this infinitesimal box with side dx, dy, dz, centered at r vector, finding the mass m anywhere inside of that at time t, then it's this expression over here. It's simply the wave function squared times the volume of that infinitesimal volume. I snuck in some additional notation that I think is pretty standard, but dv is the volume element, and Cartesian is dx, dy, dz. But this allows us in this form to use any coordinate system that we like. You just have to, if it's Cartesian, I've got this expression. But it could be I'm in spherical coordinates, and then I use the volume element in spherical coordinates. Other notation that you'll see, just to save from writing so much really, is d cubed r and d cubed r, and without the vector or the boldface on it. I'll generally use d script v for v as the volume, but I could use any or all of those. Well, we know with this probability interpretation that the wave function needs to be square integrable over all of space. And so what that means is that integral over all the space, if I extend these volumes up here to include minus infinity to plus infinity in every direction, then this integral has to exist. So it has to be a square integrable function. So the wave function got to be square integrable, or at least the modulus squared of it is, psi must be square integrable, so it means this thing has to exist, and that means that this a has to be a finite number. It's always bigger than 0, but it can't be equal to infinity. That would be a case where psi diverges. And so for this to be a finite number, it's going to be a real number, and it's going to be bigger than 0. But it has to be finite. And that means that the wave function has to vanish essentially in all directions fast enough so that integral can converge to a finite and be a finite number. Another way to say this is psi must be normalizable. if this A happens to be 1, integrated over all space of psi squared, then psi is normalized. On the other hand, if it's not equal to 1, we can always normalize psi by replacing psi by the square root of psi by the 1 over the square root of psi. And then psi prime would be the normalized psi. Well, pretty much like obtaining the time-independent Schrodinger equation in 1 dimension, we can obtain the time-independent Schrodinger equation in 3 dimensions by separating out the time and the spatial parts. This works if the potential the potential energy function does not depend on the time t, which is the usual case. So in that situation, I look for separable solutions to the full equation. So I'm going to separate out that this wave function, capital psi, is a function of r only times a function of t only, which I call f of t. I get the Schrodinger equation, substitute these in for psi, and then pretty clearly, if the potential does not depend on t explicitly, then this operator doesn't operate on anything in the t area, and so I can pull this function t all the way through it, and so it's just this operator, Hamiltonian operator, that depends only on the xyz coordinates, operating on the wave function. And then likewise over here, this is a function of x, y, and z, and this is only a partial derivative with respect to t, so I can pull it outside as well. And then if I divide this whole equation through by little psi, little f, all the way through on both sides, on the right-hand side, the psi's go out. On the left-hand side, the f of t's go out. And we're left with this expression and this expression on the right. And if you look at those, this is a function of t only, and this is a function of the spatial variables, r vector only. And for independent variables t and x, y, and z, the only way you can have a function of independent variables equal to a function of a different independent variable is if they're both equal to a constant. And so we get this separation constant E here. So separate it out, constant E. And of course, we had an interpretation of that as the energy, total energy. And we'll do that here as well. But we set this side equal to E and get this equation, set this side equal to E and get this one. And E is, at least at this stage, is the constant of separation. You can rearrange the top one into this form. And in that form, that indeed is the time-independent Schrodinger equation in 3 dimensions. It looks very similar. The only difference is this operator operates on a wave function with x, y, and z, say if we're in Cartesian. There's no time in this, and so the solution to this equation is called the stationary state. It is can be labeled though by different energies or different separation constants. The second equation here, well, we can solve that like we've done before. Here's the second equation. And I divided through by, or multiplied through by minus I and divided by h bar to get those on this side, and then realized that this is just the derivative of the logarithm of f of t, so it's a logarithmic derivative. And then I can integrate both sides with respect to t, indefinite integral, so this just becomes a natural log of f. Integrate this with respect to t, I'll get a t plus an integration constant, which I'll write in this form, natural log of a constant is also a constant. And then exponentiate both sides to get f of t is this form, a e to the minus I e over h bar t. And pretty obviously, this f of t here has an a in it, but I can absorb that into this function here. This is still a function to be determined, so I'll absorb this a into this. And that's the way most people do, and simply write the separated wave function now in this form. And then, if you're really noticing things, this E, I'm going to be solving this equation for specific values of separation constant, and so I really should probably label these stationary states with this E. And I do that down here just to make things very clear, because in general, each solution you'll get for the Schrodinger equation, the time-independent Schrodinger equation, will depend on E, and to get the full wave function for that particular solution, I have to multiply it by the specific value of e to the minus I e over h bar for that specific value of e. And then to get the total solution, the most general solution, I have to sum over all those possible e values. For us, e is energy, and so these will be the energy eigenvalues. If it's discrete, if the energy is discrete, then it's a summation. If energy is continuous, then one has to do this infinite sum in this integral form. Well, usually one starts with the time-independent Schrodinger equation in 3 dimensions, is this form here. Oftentimes they'll leave off this e, it's implied on the subscript, but I put it in here. And there is the time-independent Schrodinger equation. You solve that, and then you can get the general solution by putting that solution in up here and doing these sums for the general solution. So it's very, very similar. The only thing that complicates things is I've got a multi-dimensional function here. So it's a function of several variables. Whereas before, this was just an ordinary differential equation. It only depended on x. This operator used to only be derivatives depend on x. Well, now it depends on in general, all of the variables x, y, and z, or r, theta, and phi. So usually, one in any given problem, one selects a potential energy that we're going to study. That's the potential energy led to by whatever the physics of the problem is. And if it doesn't depend on time, we jump right to this and solve this time-independent Schrodinger equation for these stationary state wave functions.